welcome everybody to this EURASIP webinar. So let me first introduce you EURASIP, which is a non-profit organization to promote the multidisciplinary field of signal processing, both in Europe, but also beyond. EURASIP is governed by a board of directors, among which Nelly Pustelnik assumes the responsibility for our technical programs and memberships and coordinates the organization of these monthly webinars. So EURASIP has 8 technical area committees covering all the fields of signal processing, and I am Barbara Pascal, a CNRS researcher in Laboratoire des Sciences du Numérique de Nantes in France, and I am participating to the theoretical and methodological trends in signal processing TAC, which is shared by Johan Altman and Abderrahim Halimi, and which notably covers statistical signal processing, optimization, and signal processing on graphs and networks, which are the main topic of today's webinar. So before introducing our speaker, let me first describe how the webinar will be organized. So first, we will listen to Remy for 45 to 50 minutes, and then this presentation will be recorded and available on the YouTube page of EURASIP. And then recording will be stopped for an question and answer session, which will not be recorded. So now that we have the program, let me introduce you Remy Flamary. So it's really a pleasure to listen to you today. So Remy is a professor at École Polytechnique in the Centre de Mathématiques Appliquées, CMAP, and is the holder of a High Paris Fellowship in Artificial Intelligence. So previously, he was an assistant professor in Université Côte d'Azur in the Lagrange Laboratory, and a holder of a chair in artificial intelligence from Troisia Côte d'Azur, a Center for Artificial Intelligence. So he received the engineering diploma in electrical engineering and a master's degree in image processing from the Institut National de Sciences Appliquées de Lyon in 2008, and a PhD degree from the University of Rouen in 2011, and finally an habilitation to direct researches from University Côte d'Azur in 2019. And his current research focuses on including signal and image processing with framework compatible with the use of graphs. And in particular, he recently worked much on applying optimal transport theory to machine learning with a great emphasis on graph signal processing and domain adaptation. And I would also like to emphasize that Remy Flamary is really working hard to have some codes available and to have some good practices for coding, for machine learning and signal processing. So now, Remy, the floor is yours for the next 45 minutes.
It's not loading. Okay.
So thank you. I'm going to first thank Nelly and Barbara for inviting me. It's a pleasure to be here. I'm going to talk today about optimal transport for graph representation. And so we're going to talk a little bit about unsupervised learning, graph prediction, and neural optimal transport solvers, which have been becoming important aspects to actually solve optimal transport in large scale. So first, I mean, this is the obligatory slide, you know, graphs are everywhere. And of course, we need to process graph, we need to process data on graph, we need to do machine learning, we need to learn from those graphs. So there are tons of graphs. Okay, you can look at, of course, at as a molecule can be seen as a graph, 3D meshes or specific type of graph, brain connectivity to gen regularity network. Basically, a lot of data can be modeled as graph. And so the way we've been working on graphs for many years is by looking a lot at the signal on the graph and the Fourier-based representation of this signal on the graph that is usually using the Laplacian matrix. But when we do that, basically what we do is we separate the structure that is in the Laplacian matrix and the signal, that is, the features on the nodes of the graph. And that's a very powerful thing, because then you can, apply the structure, which is basically doing graph convolution. You can do nonlinearity, and that's basically the basis of all those graph neural networks nowadays, which is a very powerful thing to look at, and it works extremely well in practice. But when you do that, you tend to focus on individual nodes, you process individual nodes, and you basically alternate between updating local signal, with nonlinearity, for instance, and transferring information along the graph, with some kind of a diffusion or discrete diffusion. The thing is, when you do that, you never look at the same time at the structure and the feature on the nodes. And so that's something that can be done. Okay, there are a lot of work that actually look at the graph as a whole object, okay, with structure and features at the same time. For instance, all people doing discrete graph, which is graph edit distance, you look at the whole graph because you try to find similarity between two graphs. And so there's another way to look at that, which can be seen as maybe as a relaxation of those discrete way to look at the graph, which is based on optimal transport. That is, instead of looking at the graph as nodes and connectivity between the nodes, you look at the graph as a distribution that encodes both those connectivity and those features. I'm going to tell you what I mean by that in a sec. Okay, so the way it's going to be organized. First, a quick introduction to optimal transport on graph. I'm going to talk to you about what's called the Gromov-Wasserstein distance. Then we're going to talk about how it's been relaxed to allow for some types of application. We're going to talk, of course, about graph alignment and how it can be used for graph alignment. The second part, we'll talk about machine learning on graphs, so some applications of machine learning on graph, with a focus on one that is very interesting, that is structured graph prediction, when you want to learn a machine learning model that actually predicts an object that is a graph. So you have anything as an input, but you want to predict a graph. And so we will see that this works well, but it does have some limits, especially in terms of scaling. And so the last part of the talk will be about how we how we use neural network to speed up processing, to speed up solving of optimal transport on large data sets and large graphs. Okay, so first, as I told you a few minutes ago, we're going to look at the graph as a distribution. And so this is an important way to look at it, is that when you look at the graph as a distribution, you have the nodes that can be seen as individuals in the graph, okay? So you can see that as a discrete distribution where each node is a Dirac, okay? On the nodes, you have features, Fi, so that are basically the color. Can be, if it's a molecule, it's whether the atom is a carbon or something else. You have the structure of the graph that is encoded so as a pairwise relationship between the nodes. I will come back to that. And since it's a distribution, even better, a probability distribution, it has to sum to 1. So you have weights on those nodes. Okay, and so you have different ways to look at it. If you just look at the structure, you have weights on xi that encode the structure. If you look at the marginal on the features, you have weights only on the features, or everything jointly here, where you look at the joint features in the x and structure in the x and features in the f. Okay, so if you want to represent a graph, you need a pairwise matrix D that encode the relationship between the x, can be a distance or something else. I will give you examples. A feature matrix F that encode the features on the nodes, and a weight vector A that sums to 1 that tells you about the weights of the respective nodes in the graph. So there are different ways to look at this pairwise matrix D in a graph. Usually you can use adjacency matrix, which is a binary matrix that tells you whether two nodes are connected. You can use a Laplacian, also a standard way to do that. Or you can use something a little bit more involved because it requires computation. That is the shortest path. It's going to tell you how many jumps you need to go from one node to another one using the connectivity. And so when I'm talking about a graph from now on, I'm talking about an adjacency matrix or a shortest path matrix, weights on the nodes, and sometimes, if it's a labeled graph, also a feature matrix. Okay, so let's start first with just a graph without features. So you only have the pairwise relationships. So the matrix D and D prime are going to describe the graph on the left and on the right, okay? And so if you want to measure a similarity between those two graphs, there is something that is called the Gromov-Wasserstein distance that will allow you to measure how similar those graphs are. And the idea is to say, if two nodes are close on the left, I want them to be transported to two nodes that are close on the right. If two nodes are far away, I want them to be transported on two nodes that are far away. Okay, and so that's the intuition. And how you do that? Well, you solve what's called an optimal transport problem. That is, you search for an optimal transport plan, that is a matrix, that will move mass from the left graph to the right graph. And so this matrix has constraint that you can see here that says that if I sum the column of the matrix, I recover the mass on the left. If I sum the line of the matrix, I recover the mass on the right. Okay, so it's a transport plan. That's the constraint to make it a transport plan. But you don't want any transport plan. You want the transport plan that minimizes the divergence, basically that minimizes the difference between the pairwise relationships. Okay, so you will measure how close those pairwise relations are, and the matrix will appear here, and you will optimize over this matrix. Okay, so I'm going to show you a quick demo of this. Basically, you're going to have some graphs. So this is one graph. So two nodes that are close, one that is far, okay, and another graph, okay? And if you solve Gromov, Gromov is going to give you a matrix that will tell you if you transport mass from one point to another one, and it's going to do a black line between the point where mass is transported, and no lines if it's transported. If you solve Gromov, this is what you get. That is, the 2 points that are close are transported to the 2 points that are close, the one that is far away transported to the one that is far away. Okay? And interestingly, since it only looks at pairwise relationship, the solution of the optimal transport plan, as you can see, is invariant to rotations. Because if you look at just distance matrices, or if those points are connected, a rotation won't change the connection, and so the plan is the same. Okay, great. So when you do Gromov, you want to solve that. Basically, you want to move mass, you want to transport points onto points that have the same neighbors. Okay, so if one point is in a dense area, you want to transport it to another dense area, and vice versa. To solve this problem, so this problem is a quadratic program. It's not easy to solve because actually it's a quadratic program which we tend to love in optimization, but it's a non-convex quadratic program. So it's basically you cannot really be sure to find a global solution, but there are algorithms that actually solve this problem. Frank-Wolf algorithm, for instance, that can be used to find a local optimum of the problem. And of course, there are variants of this, so I won't enter into detail here, but there are anthropic regularization that were proposed sometimes to speed up this. When you regularize this problem with entropy on the plan T, it densifies the plan, makes it a little bit more convex, and you have algorithms that can be used to speed up the process. But it's going to densify the plan, which makes it maybe less efficient on some application. Okay, so that's for Gromov. Here, I'm only looking at the structure. Okay, I'm just trying to align those pairwise relationships, those adjacency matrices, or those distance matrices. But in practice, sometimes you also have another information. Between two molecules, of course, the structure is different. So you cannot really, compute the similarity. So you look at pairwise relationship between the structure of two molecules. But the type of nodes, whether it's a carbon and hydrogen, this one is shared between the two spaces. So you can measure a similarity, and you can provide a cost to move, from one carbon to an hydrogen. So now you have two aspects in the graph. You have the structure that is encoded in D, okay, and the features on the nodes that you can encode in a distance matrix. It's going to cost you to go from one point on the left graph to one point on the right graph. And so the fused Gromov-Wasserstein is an extension of the Gromov-Wasserstein distance that encodes simultaneously the structure and the features. And you have alpha, that is the parameters that weights more the structure or more the features. And as long as you have both, basically you want to find a graph, you want to find a mapping, an alignment between the graph that respect both the structure and the features, the best possible alignment. Okay, Great. So now what do you do with that? Well, one crazy thing that you can do is, for instance, finding correspondences between surfaces. If you look at those surfaces, they are graphs, okay? They are actually triangular surfaces, so they are a graph, and you can compute a shortest path, along these graphs, okay? Some kind of geodesics on the surface, and you can take one surface, another one, and when you solve, you can say, where does the mass from this point goes? And you can see that it goes to somewhere else. So it's quite impressive here because you move from one part of the body to another part, even if the surface is extremely different. It will also work on this one, which is just barely humanoid. And it still respects, the foot goes to the foot, the head goes to the head. So it's very powerful to do alignment in a non-supervised way. And you can even map from one 2D surface to a 1D distribution here, and you can see that it still preserves the relationship. So that was one of the first illustration of how Gromov is very powerful because it can preserve pairwise relationship. Other types of application is being used, for instance, to find correspondences between word embeddings. So you basically embed words in French, you embed words in Italian or in English, okay? So you're in different languages, okay? So you have no correspondences between the two. But by looking at just the pairwise relationship between the word on the left and the pairwise relationship between the words on the right, by doing Gromov, you're going to allow to find correspondences across language, and it works quite well, actually. For instance, the one here, the word one is mapped to the word uno in Italian. So basically, by doing totally unsupervised relationship, unsupervised alignment, you still recover things that preserve the geometry and that makes sense. But in practice, the thing is, if you go back here, you see you have constraint here. I told you all the mass from the left needs to be moved to the mass from the right. Okay, that is, you need to transport the whole distribution. This is a very strong constraint because, you need to put weights on the nodes, which is very hard because some graph, you just have the graph and you don't know how to weight those nodes. And that's a very difficult question. And if you're unsure about those weights, the idea is to say, well, maybe I don't need to map everything perfectly and I can relax those constraints. I don't need to move the whole mass if it costs me too much to move the mass. Okay, and so this is called unbalanced Gromov-Wasserstein. That is, the constraints on the marginals, the constraints on the left and right marginal of the OT plans are put here, as penalization. And so you have another parameter that measure, how much you relax those things. So that's one variant, and you can go a bit further. You can totally relax one side, which allow you to do something. I'm going to show you. I'm going to come back here. Okay, so I'm going to show you a very simple example. Okay, when I do that, you have two Diracs on the left and two clusters on the right. Okay, and what you can see is that basically all the points of those clusters go to this cluster. So Gromov can be used in a way, to do clustering because those are close, so they should be mapped to the same point. If you want to preserve the pairwise relationship. But the problem is, if I put one more point, look at what happens. Because of the marginals, this point does not have enough mass to fill a whole cluster. So you need to take mass and then you break the clustering. Okay? And so the thing is, if you relax this marginal, okay, I'm going to try to run it now. If you relax the marginal on the right, okay, it will allow you, I broke everything, so that's bad. I'm going to try again. Okay. Okay, great. So now, okay. So look, here I have two clusters, and the one on the right is reweighted. Okay, and if I add more points, look at what happens. Basically, the one on the right is going to take more mass. So it's still optimal transport, but you relax the marginal so that you can better fit the data. Okay, and here is the same. Okay, so now why is that important? Because in some application, the mass is changing. And one very important application, one that I like a lot, is to try to find correspondences on biomedical data on functional MRI. So you measure functional MRI between two different persons, okay? And the thing is, we each have a different geometry in our brain, okay? So it looks the same, but if you look in detail, the surface is different between here and here. And so it's very hard, to say, oh, this area corresponds to this area. So historical methods, they just take the surface of the brain, they blow up like a balloon, okay? So put it on a sphere, basically, and they blow up both, and they find correspondences like this. But the thing is, those correspondences, they don't take into account the signal on the surface, okay? And so by doing optimal transport between the two, the optimal transport plan will align between those two surfaces by preserving both the geometry of the surface, which is the Gromov part, and the activation on the different areas on the surface, that is the signal, that is the features, that is the Wasserstein part. And so by doing both simultaneously, you can find correspondences between the brain of different persons. And so what we did is that we estimate those kind of plan, but the thing is, the area of activation for one person and the area for another person is different. So if you have different surfaces, of course, you need to adapt to those surfaces. You cannot keep the constraint. You know, it's like my example before. If you have more points in a cluster, you shouldn't break everything. And that's basically the same idea. And by relaxing those marginal, we found far better correspondences between the brains. And one application that was quite nice is by using contrasts, so activations during functional MRI, so people are doing some mental tasks, we find the correspondences, and then we apply this plan on new mental tasks, and we try to predict the activation of the brain of a person by using the measurement on another person. And so this is one way to measure how good our alignment is, because it's like a predictive way. If we can predict the activation, it means that we did good alignment. And so the baseline was at 25% Pearson correlation. And by using Fugue, which is fused and balanced Gromov-Wasserstein, you can gain up to 10% in terms of Pearson correlation. That shows that we have a better alignment, at least in a predictive way. Okay, so that was the first introduction. So I hope you understood the intuition. What is Gromov? Basically, an optimal transport problem that tries to find correspondences between two graphs by preserving the pairwise relationships and the signals at the same time, but by looking at the graph as one object that is a distribution. And so the thing is, now this gives you an optimal transport plan, so it gives you correspondences, but also it gives you a way to measure similarity between two graphs. Because if the Gromov-Wasserstein is 0, it means that you have the same object. If the Gromov-Wasserstein is larger than 0, it means that you have different objects. And so it's a metric, so we can prove that it's a metric. And so you can use it also to do what's called barycenters. Okay, so when you do barycenter in the Euclidean space, what you do is called the weighted mean. Okay, so basically you put weight and you want to minimize the sum of the weighted distances up to different corners, if you want, on the triangle. When you do that in Gromov-Wasserstein space, you do what's called a barycenter or a Fréchet mean. Okay, and so by putting weights on the different graph, you can basically interpolate between those graphs in the geometry of Gromov-Wasserstein, which is called the metric measure space, which I won't enter into detail, but I'm really open to question if you're curious. And so you can solve this, and so you can basically interpolate or compute average of graph. I'm going to show you an example here. So if you look at those 8 graphs, so it's circular graph with noisy signal and also noisy collection. And so if you compute a barycenter of those 8 graphs, you're going to recover this. You're going to recover here, you have 2 different barycenters, one with a larger number of nodes and one with a smaller number, because when you compute the barycenter, you can actually select the number of nodes, because Gromov can be applied between graphs with different number of nodes. Okay, so you can do both computing an average of a graph, but also doing some kind of graph compression, representing it with left nodes. So that's an example. You can do that on slightly more complex graphs. So those are 8s here, okay? And those are the barycenters. Great. So if you can compute the barycenter, probably you can do a mean. And so you can do some extensions of algorithms that require a mean, for instance, k-means, okay? So now if you have a data set with different types of graph and you do k-means, that is, you assign the graph to the closest cluster and then you update the cluster using fused Gromov-Wasserstein metrics. Okay, so you compute the barycenter, and then you do that again. You're going to converge, and you can do k-means in the space of graph. There are other types of application of Gromov-Wasserstein, that is, fused Gromov or Gromov-Wasserstein measure similarity between two graphs. So you can use it as a data fitting term to compute actually dictionaries. And so you can learn a vector representation of a graph in a dictionary. So you can learn linear dictionaries, which is this paper here, or you can learn more complex nonlinear dictionary, where your representation of a graph is actually the weights on the dictionary, and you compute the barycenter with those weights. Okay, so now you're in a more complex manifold. It means that if you want to reconstruct a graph from the dictionary, you need to solve a barycenter. And so that's one application. So you can do representation learning. You can learn dictionaries, very simple dictionaries from dataset of graphs. You can also use this distance as a way to perform what's called graph pooling in graph neural network. That is, when you do graph neural network, you update your graph representation. So you do basically you update the feature locally, and then you spread information on the graph, and then you update again. But usually, if you want to do classification at the end, you need to pool it. That is, you need to go from one graph to one vector. And so by doing that, you can pool it by just computing distance to templates. And so the vector of distance is a representation of your graph. That is, if you're close to a template that corresponds to one class, obviously it's going to give you some information about if you can predict the class afterwards. So this is a pooling that allows you to go from node representation to vector representation of a graph for an end task. Okay, but another application that is very important, in my opinion, is supervised graph prediction. So supervised graph prediction, the objective is to learn a function f, so it's a supervised machine learning task, where you want to learn a function that takes something an input and will predict a graph. Okay, so there are many questions of that. For instance, knowledge graph extraction can be nice. For instance, you put a text as input, and from the text you try to extract knowledge, and then you have a knowledge graph. In natural language processing, there are also those questions. When you have a sentence, what's the organization of the sentence? What the types of words? So that's also a graph. Molecular identification in chemistry. So this one is quite nice. You can do that in a CSI something where they do what's called the spectrum of mass, and so from the spectrum of mass they recover what was the molecule, and they can find someone afterwards, these kind of things. And so this is a very challenging problem, but it's also very important. And so what people do to do that, for many years they used what's called surrogate methods. That is, they compute an embedding of the graph outputs, an embedding of the input, and they map between those two embeddings. So basically by using neural kernel methods, for instance. And so for many years, those were actually state-of-the-art methods. But the problem with those methods, it's a problem, it really depends on the application, but one limit of those methods is that it actually does not really give you a graph as output, give you an embedding of a graph. And then you need to come back to the graph. And this is a very difficult task. It's called the pre-image, okay, which is difficult in vector space, but even more difficult maybe on graph space. And so we try to think about one way to solve this problem. And one way is to say, you remember, I told you can do barycenters and you can interpolate between graphs. Okay, so basically, what I'm trying to tell you is that if you want to predict a graph, maybe what you should do is not predict a graph, but predict weights on a barycenter, and then you can compute the barycenter that will recover a graph for you. And so that's something we proposed a few years ago. And so basically now you can do one neural network that goes from the input, here a spectrum of mass, that predicts the weights on the barycenter, and from that you can solve the barycenter and predict the graph. And so it's just, you use the Gromov-Wasserstein as data fitting term, and you use the barycenter as a model to reconstruct your graph. So it's very nice, it works. So that's a simple example, for instance, where, we want to predict a graph, and the input is basically the number of clusters you have in your graph. Okay, so that would be the true function, So you see clusters appearing one by one, and it's like more or less connected. And so we could learn a continuous function that, when you threshold afterwards, allows to learn also those kind of relation. We also apply that on molecular, but the thing is, it's very computationally demanding, because you need to solve a barycenter every time you want to predict something. And so that was a limit of the method, because you couldn't actually scale on very large data set or large graphs. And so in practice, what you would like is to use deep learning to have an end-to-end pipeline that takes something as input, can be a vector, can be a spectrum, but the output is already a graph. And so basically you want to predict a graph. So basically you could say, I just want to predict an adjacency matrix, but the problem is you need to be able to predict graph of different sizes. Okay, and that's the challenge. So in order to do that, maybe what you could do is instead of predicting different sizes, you can predict a graph of fixed sizes, big enough, but also predict a masking. Okay, that is, if you have two nodes, you can predict an adjacency matrix of size 3 times 3, but mask all the nodes that are irrelevant. Okay, so now the output of the neural network could be that one binary matrix, that is the adjacency, and one masking matrix that actually tell you which nodes are active. So you can take an input, you can design a neural network that will predict you a matrix of size 3 times 3 that contains probability of connectivity between the nodes, and a matrix of size and a vector of size 3 that tells you the probability that this node is actually active. Okay, but then so that's the output of your neural net. It's a continuous version if you want, and that's what you want to predict. And then if you want to fit that, you need a loss. You need a way to measure the similarity between your prediction and the true data. Okay, and so basically designing this loss is not that easy. And one important aspect of designing this loss is that you want to be invariant to permutation of the nodes, okay, which is basic in graphs, because if you permute the nodes and the features at the same time, you recover the same graph. And so you need to have a loss that is invariant. And interestingly, since in optimal transport, you look at distributions, distribution is a weighted sum of Dirac. There is no ordering on your Dirac, so you're naturally invariant to node permutation. And so what you want is actually a loss that is invariant to permutation, so that you can fit your neural net, and then you have your neural net, you just do a thresholding, and it's going to predict your discrete graph. So this actually already existed. So in 2022, Schitt and collaborators proposed an architecture that does that in a way. So it takes an input. So here in this paper, it's mostly images. Does a transformer, so with cross attention, okay, and predict node embeddings that allows to predict both features on the nodes and pairwise relationship between the nodes, which they call relation head, predicts the adjacency matrix, and object prediction predicts the type on the nodes. But what they did is, to be invariant to permutation, they used an Hungarian algorithm to do linear assignment between the features. That is, when they try to find correspondences, you know, between the left and the right, they used linear optimal transport, which means that they totally discard the structure when they find the alignment. And then they put it in a loss that put the structure again. And so this is suboptimal because the optimal plan they're going to recover only works on the linear part. It's not optimal for the quadratic part. And that's basically why we proposed what we call the any2 graph framework, which is very similar framework, but using optimal transport on the graph, as I discussed, but an optimal transport that aligns simultaneously the structure and the feature. And basically, the architecture is very similar. So you have an encoder, then a transformer with encoder, decoder, and cross attention. And then we have a graph decoder that predicts the adjacency matrix, the feature on the nodes, and the masks. That should be 1 when the node is active and 0 when it's inactive. And by thresholding the mask, you know how many nodes you are and which nodes are there. And by thresholding the adjacency matrix, you recover actually the structure between your graph. So now, what was the loss? So the loss, originally, we wanted to use the fused Gromov, because fused Gromov even works, you know, with graph of different sizes. But it was actually a problem because fused Gromov, I won't enter into detail, but basically you can have a 0 fused Gromov and still predict something that is wrong. Okay, so it's not well defined to handle all those 3 aspects. Okay, so we proposed what's called the partially masked fused Gromov-Wasserstein, which is an extension of the fused Gromov, where we have a data fitting that fits the padding. Okay, so this one is linear. A data fitting that fits the features, but that is masked by H. The intuition is very simple, is that if you assign one node to another node, but the node on the right is masked, it shouldn't appear in the loss. Okay, you basically discard. It's like you have missing data. Okay, this prediction, you don't care what the value is because the node is masked on the right. So you can mask it on the right side. Okay, and so we also extended the structure loss, where now we look at all the pairwise relationship by masking it again from the right. Okay, so the right part is the true data, and the left part is the predicted data, this continuous version. Okay, and so this loss is interesting. It's basically a generalization of the fused Gromov. It can be computed is M3 log M, so it's iterations. So one iteration costs M3 log M, and there are usually few iterations to converge. So it does not scale that well to large graphs, but it's invariant to permutation of the nodes, and it's a very good loss. I'm going to show you why. On the right, so this is a very simple graph, okay? So it's basically just a connection between two nodes, okay? And with feature F1 and F2 on the nodes. And if you look at the prediction, here we predict a graph of size 3. So one node too many. So we should, at prediction, discard one of the nodes. And so if we put a D like this with A, parameter A, 1 minus A, and weight H, 1 minus H, okay, and we repeat here the features, okay? Basically, what I'm trying to do is the minimum is when you put H, 1 and 1 here, okay, or 1 here, and A, 1 here, and or 1 here, okay? So basically, when you're in a corner of AH, you're happy because you predict the right graph. When you're in this corner, you're not happy at all because you basically connect points that do not have the proper features, okay? And so this is the loss we proposed, and this is the edit distance. And as you can see, the PMFGW is actually a continuous relaxation of the edit distance, where you do have indeed zeros on the corners where you want to predict, but this is differentiable, and you can actually optimize this. Okay, and so in terms of architecture, it's actually quite simple. It's transformer, so if you know what it is, with attention, okay, and cross encoder, that is, the input can have any size, but the output has a fixed size of size M, that is the maximum number of nodes on the right. So basically, whatever the size of the input, we will always predict M nodes. And so we're going to have node embeddings, and we will use those node embeddings to predict pairwise relationships, features, and masking. And so all those are MLPs, and you just need to optimize the parameters of these MLPs jointly with the parameters of the transformer. And it works very well. That is, if you want to predict, a connectivity graph from this image, you can see that the true graph is like this. This is our output, and this was, the paper of sheet. It's called relation former. It does not work very well on some application. If you want to predict, a map from a 2D image, a binarized 2D image, it also works better. And it also works very well to predict molecules from chemical description of those molecules. And so we were quite happy to have this. So really nice, very small edit distance, which means that we predicted the graph very well with any two graph. But the thing is that we still have a lot of challenges here. And the challenges are very clear. If you want to predict molecules, they can get big, okay? If you want to predict plans between brains, obviously, you're going to have high resolution stuff in MRIs, okay? And so basically, you have large graphs, and the thing is solving optimal transport scales cubically with the number of nodes. So it's not something that you can do on very large graph. Okay, even traditional optimal transport is hard to do on large distribution, but when you add the Gromov part, it's even worse because you need to look at all those pairwise relationships. And so there are approximate solvers. As I told you, you can do entropy. Entropy will make the problem different. It won't solve the original problem, but it might be seen as a good approximation. But the thing on graph is that entropy will spread mass, which means that, if you look at similarity between two molecules and the carbon is actually spread between alpha carbon and an hydrogen, this is weird, okay? If you have one carbon, you want it to be mapped only to one carbon. You don't want to spread the mass on the neighbors of the carbon. And so entropy is not really optimal in some applications. So people in machine learning have looked at how to speed up things, and they used by using neural network. The idea is an optimal transport plan is a big matrix with lots of constraints. Okay, so basically, it's hard to solve this big matrix. So what people have done are actually parameterize the plan as a neural network. And so now instead of solving over T, which is an extremely large matrix, you can solve over theta, which is the parameters of neural net, which might be easier to solve. So that's called neural OT, neural optimal transport. So that's one first strategy. But the thing is, when you do that, you still need to solve for every pairs of graph, you still need to optimize a neural net. Okay, so it still is not going to scale if you have a very large data set with millions of graphs. Okay, so what we propose to do, the philosophy of what I'm going to present next, is to say, okay, maybe I don't need to solve independently all those optimal transport. Maybe I can learn a neural net that will predict for me the optimal transport plan when I give it the graph as inputs. Okay, so before you just optimize the transport plan for one pairs. Now I'm going to try to find a neural net that can predict for all possible pairs the optimal transport plan. Okay, and so it's called amortization. Basically, instead of solving the problem, I learn to solve the problem. Okay, and so we did that for two directions, which are complementary, and I'm going to present shortly in the next slides. First, with extremely large data sets of small graphs. Basically, we went to several millions of graphs. So when you do one epoch, you go on millions of graphs. And so we learned a neural net that can predict the loss and the optimal transport plan for those small graphs. And we learned that also on larger graphs, but with maybe less pairs on the brains. Okay, so for millions of graphs on relatively small, it's on molecules. And for large graphs, we apply that on the brain. And I'm going to present that now that I'm here. So you should recall that I presented the any2graph framework that allows you to go from anything to a graph as output. So in this paper, we call graph level autoencoder, GRAIL, okay? We try to learn an autoencoder that takes a graph as input, encode it as a vector, and then reconstruct a graph. So it's very difficult, especially since to reconstruct the graph, you need to use a loss that is invariant to permutation again, that is an optimal transport loss. Okay, so what we proposed to do was to, when you train an autoencoder, you train F, that is the encoder, and G, that is the decoder that reconstruct the graph. We propose to learn simultaneously not only F and G, but F, G, and M, that is basically a model that predicts the optimal transport plan for you. Okay, and I'm gonna, the idea is instead of minimizing individually each pairs of graph, you just plug M with the graph as input. Okay, so basically M takes as input node embeddings of the nodes on the right and on the left, and it's gonna find you automatically a permutation, correspondences between those nodes. Okay, great, and it works very well, actually. And when we compare to state-of-the-art graph autoencoder, so this is the edit distance, okay? So for simulated data and coloring, we have an edit distance that is nearly 0, and GI accuracy that actually measure if we predict exactly the proper graph, which is 99. So we have a perfect embedding, okay? Near perfect reconstruction, which is much better than state-of-the-art autoencoders. And then we did that on much more difficult data, that is molecules. So PubChem 16 is all molecules up to size 16, and PubChem 32 is all molecule up to size 32. That is, PubChem 32 is 80 million graphs in the training dataset. And so by using GRAIL, that is learning simultaneously the solver, the optimal transport solvers, the encoder and the decoder, we could train an encoder for those graphs that has an edit distance, an average edit distance smaller than 1. That is, most of the time you actually predict exactly the proper molecule when we encode it as a vector and then reconstruct it. And so what you can do now is, since you have an encoder, you can encode a graph, encode a second graph, do a weighted sum in the embedding, and then decode it again. Okay? And when you do that, what it means is that you're gonna interpolate between two graphs. It allows you to do these kind of things. Something else that we did, you can also compute an average, okay, a barycenter, because you encode everyone, you compute the average in the vector space, and then you decode. So it gives you an average. And something else we did, which was nice, is we did it on those graphs, for instance. We learn in the embedding of the encoder a regressor that predicts the size of the graph, the number of nodes. Okay? And then we take one graph, we embed it, and we do a step on the gradient of this predictor of size, which means that you go in a direction in the embedding that's going to increase the size of the graph. So you do one step, and when you reconstruct, your graph has one more nodes. And then you do a step again, and then your graph has one more nodes. So basically, you can do semantic editing of your graph. If you can have a classifier or a regressor in the embedding, you can edit the graph like this. So that was the Grail paper, which is interesting. By the way, we have a code and we have a model on Hugging Face, so you can just load the model, encode molecules, do stuff, and decode molecules again quite quickly if you're interested. Then we looked at the brain. So if you remember the application on the brain, unbalanced was important, okay? Because the area of the brain of someone can be different in terms of surface as the area on the brain of someone else. So you actually need to do unbalanced OT, not exact OT. You're not going to find one-to-one correspondences between brains. And so what you want to solve is actually this, if you remember, the Gromov term, where you want the structure to be preserved, the Wasserstein term on the middle, where you want the features to be preserved, and you penalize the violation of the marginals. And so in this paper, which we called ULOT for unsupervised learning of OT plan, what we do is we actually minimize, we train a neural network that predicts the optimal transport plan. But a nice feature of the neural network is that it's actually conditioned by alpha and rho, which are parameters. Okay, so what it means is that we learn a neural network that can predict all the solution of the optimal transport plan for all the parameters alpha and rho. Okay, so that's nice because in a way, when you change alpha, it's the same data, but it's a different optimization problem. So it's some kind of data augmentation. Even if you don't have that many pairs, you learn something continuous as a function of alpha and rho. And so what's interesting also is that you're differentiable with respect to alpha and rho, and you can do nice things. For instance, so you can predict the optimal transport plan. Okay, so that's nice. As a function of rho, as you can see, when rho is large, you respect the marginal, you need to move everything. When rho is smaller, you can move only part of the mass. So here we had a green cluster and a red cluster. Here you have a green and a blue. So obviously you want to move the green on the green, but the red not on the blue because the features are different. And with ULOT, you can do that when actually the numerical solver actually failed to do that because it gets stuck in zero. Okay, that's of course an example we picked, but still it happens that the ULOT solver works better than the exact numerical solver. And even better, we are smooth with respect to alpha and rho. That is, you have parameters, alpha and rho, you know, that are important. So, am I going to use more the structure? Am I going to use more the features? And now you can actually optimize those alpha and rho with respect to a quality of your estimator. So it allows you to do some kind of B-level optimization where you can have a validation set where you optimize alpha and rho given that because you already learned a solver, ULOT, that gives you the plan and that is continuous with respect to alpha and rho. But one of the most important aspects is that actually the solver ULOT that uses neural net is extremely correlated with the numerical solver. As you can see, here we have a Pearson correlation of 0.99, okay, between the numerical solver and ULOT. Sometimes ULOT is better, sometimes numerical solver is better, okay, especially for large values. But it's very, very correlated. So we were really happy to see that. So basically, we have a good optimal transport plan. It's not always the best one, but it's a very good one. And more importantly, it's extremely fast. Okay, basically, if we compare to numerical solvers, even the anthropic ones, which are considered to be state of the art to approximate OT, we can be up to 100 times faster because we just go through a neural net and we predict the plan instead of actually doing iterative optimization. For equivalent error, we can be much, much faster, 2 orders of magnitude. And then you can actually predict correspondences between brains much faster. Okay, so For instance, here you see the source and the target brain, so two people. And when you map the source onto the target, this is the kind of thing you recover. So it's not perfect. Actually, it's normal that it's not perfect, but you can see that a lot of the areas are activated the same, except this one, because basically in this brain, you don't have red at this part, so you cannot actually read at this part. Okay. So now, what I try to explain to you is first, quick introduction to what is Gromov-Wasserstein, what is optimal transport between graphs, between distribution that live in different spaces. Gromov-Wasserstein and extension. Okay, the fused Gromov is going to work with labeled graph. The unbalanced fuse will adapt, when you have, for instance, one cluster on the left and not on the right. And all those extensions, of course, you need to pick the proper one for your application. Keep in mind something, the weights, if you do OT, optimal transport, the weights are important. And so either you have information on the weights, you know that this node has this measure of importance, and you can just plug it and everything is perfect. But if you don't have information, now you have a question. I'm going to put uniform because that's what everyone does. But is it a good idea? And that's where basically doing relaxation of OT will help you basically handle the case where you're not really sure about the weights. And you can do very nice thing. You can measure similarity between graphs of different number of nodes of different size. You can then use it as a data fitting term to actually train predictor of graphs. You can learn autoencoders, so you can do unsupervised learning on those graphs. And keep something in mind, OT can be costly numerically. And so now the trick that has been proposed recently to handle this is to do what's called amortization, that is, learn neural network that can predict solution of OT. So not exact solution, but good enough solution for your task. So I want to thank all my collaborators on graphs because I had the chance to work with tons of very, very wonderful people, a lot of them being my PhD students. And so keep in mind also, if you want to do optimal transport, there is a toolbox called POT for Python Optimal Transport. It's already used quite a lot, so feel free to use it and to tell me if there are bugs or to contribute to it if you're interested. Small comment, I should have updated this slide. I'm not looking for interns anymore, but I'm looking for research engineer or possibly postdoc, so feel free to contact me. Well, I'm done. Thank you.
Thank you very much, Rémi, for this very nice and rich presentation and for also speaking 50 minutes exactly. So if you have questions, if people do not have any question anymore, we can thank you for this.
Can I say one last thing?
Yeah.
We have an open position. Actually, we're going to have 3 open positions in machine learning at École Polytechnique, but one on graph processing. So if you do GNNs, if you do signal processing on graphs, feel free to contact me and look at the open position on the École Polytechnique website. It's very, very nice position, tenure track, and with a reduced teaching load. Okay. Sorry.
Thank you very much. And we have a last minute question about transferring learning. And so now we'll conclude this webinar by first thanking very much Rémi Flamary for this nice presentation. Many very positive comments were appearing in the chat. So I think that everybody enjoyed your presentation and that we will now all know more optimal transport and graphs and their interplay. So thank you very much. Thank you very much to the participants who attended this presentation and asked interesting questions. And I will end by a short advertisement. The next EURASIP webinar will be given by Arcontis Politis on February 26 on deep learning in spatial audio processing. So you are all much welcome and have a nice day.
Thank you, Barbara.
Thank you, Rémi. Bye.